Hey geeks! Welcome to a new video. Today it's all about hands-on experience. We are going to code together a genetic algorithm NSGA2 with my favorite package Pymoo. I hope you enjoyed the video. Don't forget to subscribe to stay up to date, and if you have other wishes about hands-on tutorials for optimization, just drop them in the comments below. So today we're going to implement one genetic algorithm, my personally favorite one, NSGA2. We will use a package for it, so it's not completely coded from scratch. I will show you how you can solve problems with a genetic algorithm in less than 30 minutes. I prepared already some stuff, so the video will be shorter. But yeah, my experiences are 30 minutes. We will have a mathematical test function today, which I prepared already for you here. Let's execute this one. So we use a package called deep, which has different benchmark functions, just that I don't need to program them our own. But you see the first functions, we have two inputs like x and y, and we have two objectives, f1 and f2. And you can see the functions are kind of different. So this function has one optimum, which is over here, and this function looks a bit more wild. And the goal is to optimize both of these functions at the same time. And to do so, we are going to use NSGA2, and let's say the inventors of NSGA2, they released a super cool package called Pymoo. And I want to show you how you use it with Pymoo. They also have other genetic algorithms, but the focus today is on NSGA2. Other videos will follow. Just for you to get a brief feeling about the benchmark function before we get started, let me show how it looks like. We imported benchmarks over here from deep import benchmarks. Yeah. So when we call now these functions that you saw over there in the same way, and we say let's look where the point 0, 0 is, you see this one is kind of optimal. You see we hit the -10, which is exactly this point here, and for this one we are at 0, so 0, 0 here is somewhere on this level. And we can now change the values as much as we want, and you see they will change as well. But the goal now is we don't want to do this manually, and there's not one best solution, but there are Pareto optimal solutions. So use this function, and how can we pass this function to find the best solutions? To do so, the first thing I'm going to do, I will import Pymoo. We want to minimize both of them, so sorry, I have a new keyboard, switch from German to English, so I'm a bit confused always. The first thing we do is we import minimize from Pymoo. Minimize is the function on the highest level that will enable us to find all optimal solutions regarding we have a minimization problem. For you to get a clear understanding what we need for that, let me write this down. So I said already we need a problem first, so we first need a problem that we describe. It's important for the algorithm to say what is the problem. Then I said it already. We also need to define an algorithm for the minimization. And the last thing we need to do, we need something like stop criteria let's call it stop criteria. So these are the three things we need to optimize, or we need to define before starting to optimize. And these are also the three things that this minimize function needs later on. So I would say let's get started with the problem itself. We also have in Pymoo a class for it. I really love that package. I mean, it's really good coded. Props to the people that maintain it. That's really nice. So we just import problem here, and with a problem we can define things now. What does a problem actually need? Yeah, it's always problem is a class. So on one side we need to tell the problem which is the function to evaluate, which is obviously the one that I showed you here. we need the problem also to tell the number of variables. So how much input variables, how much output variables we have. In this case, it's both 2. We need to tell the problem what are the borders of each input variable. For this problem, it's all 5, minus 5 to 5 for both, like you can see here. So what we do first, we build our own problem class. Let's call it problem wrapper, and we inherit from the problem class. Now, for the ones that are not familiar with it, now it's just like we build a class, but we inherit from this class. So all the attributes that this problem class has already, we don't need to code them, which makes it easier. And all we need to pass to this class now, because it's already pre-built, we need to define a function called underscore evaluate. That's exactly evaluate. Yep. And what we pass to this class is this function is also predefined, so you don't need to worry about nothing actually. You just can copy it. I will also attach the code later, the link to the documentation below. And all we have now is we do a function where we wrap exactly this benchmark here to make a call and to return then all the best solutions. It's important that, oh, I did a typo here, it's not design, it's not one design that we pass, because if you watched my theoretical video about NSGA2, it's all about, we think in populations and generations. So the genetic algorithm will always create a new population, which is consistent of not only one individual but a lot. So in this evaluate function, it expects that all of the designs, all of the single individuals within a population are also evaluated. So that's why let's do a result array which is empty. You can also write this in more clean code alternative, but for now I will do it step by step. You can also use lambda functions here, and then we say like for design in designs, so we just parse this. We say result.append, and what we append is exactly what we call the benchmarks.cursorve. So, and we pass the design to it. So the design itself is an array. It's like in the same shape as you see this here. Like that's why the design goes. So that's how one design looks like. Designs then is an array of arrays or list of lists, however you want to see it. So what we create here now is equivalent to the designs. We create an array which inherits all the results for each individual design at the same counter like the design is. And what we just need to do now is we need to, and this is like from the framework, you cannot change anything about it, but we just need to set this equal to output f. F is like for function output in this package, and set it to results. And they work with NumPy, so what I really recommend you is to, in the end, convert it to a NumPy array to be sure to not have any mistakes. So let me just do it this way. Let me see if I did a mistake somewhere. It's not append. He's complaining here for my out, but let's see if he lets me do it. So this is the evaluate function. Okay, so everything we did here, we wrapped the function call. So whatever you want to optimize, you need it wrapped somehow that you can just call it and get the results. That's super important. You can also do this within this evaluate function. Okay, so it doesn't need to be one function call. This is only the mathematical problem. I also will link in the description below how you can proceed with more complicated problems or models you want to wrap. And if you want a video about it, let me know in the comments. But for now, we just keep going with it. And now we have the problem wrapper. So let me just initialize this one. No mistakes, always good. And now we can really define our problem. Like I said before, our problem in the end of the day will be this problem wrapper class that we initialized here. And it requires now different variables to take into account. So what I said already before is the number of input variables, which is 2. It's called n bar here. Then we also need the number of objectives. You find all the docs also linked in the description below, so all the class, and what you also can do is everything here. For now, I'm just going to do it manually. Then we need the boundaries. So the lower boundary first. You always pass an array, and for each design variable you pass now the lower boundary. So for me it's -5 for this problem. Let's make a float out of it. Actually, it doesn't matter. And we do the same for upper bound array, and we go from 5. Like both variables have the upper bound 5. That's it. We have the problem defined. Let's get to the next point. Problem defined. The next one is the algorithm. Like I said before, my favorite one is NSGA2. So we're gonna stick to that one. Also here in the description you find much more different ones. I mean, there's a bunch of genetic algorithms and they're all good for something. And this one is kind of fast. We just say, hey, our algorithm equals NSGA2 in this case. And the only thing at the moment we will pass to it is the population size. It's called pop size here. Let's set it to 100. Want to see some nice results. That's it. If you want to handle mixed integer problems, or you want to change mutation rates, like if you don't want to take the defaults, all these things can be changed also within here. I'm going to do a separate video about it because it's specific, it's for the more advanced people. But if you want to do stuff like that, this is done in the algorithm class, in this case NSGA2. You can also put in constraint handling, whatever. They really take care of a lot of things. It's pretty cool. And we are gonna make our own video about it. For now, let our algorithm just be like this. Population size 100. And the last thing we now need to define is like a stop criteria or terminator. Let's call it stop criterium. Forgive me. Yeah, and this is only, you have also here different ones. For today we choose the most common one is the number of generations in every genetic one. So we say the number of generations and let it be 100 as well. So we will have 100 generations with each population having a size of 100 individuals. You see here, we have less than 20 lines of code in the end. So the most important part is to wrap the thing in a good way that you give your designs in, you do your evaluations, you can also do with parallelization side here, and then that you write the results to output f within this evaluate function. Yeah, now we have a problem. We talked a lot about how to implement it. I'm kind of, interested about results at the moment. So let us use this minimize function and see how it works. So we have a problem that we defined as a problem. We have an algorithm that we define as an algorithm. I'm boring, I know, I don't have better names for it. And we have a termination that we called, at least we have one point that it doesn't have the same name. Criteria. When I'm gonna execute it now, hopefully only if we did a mistake somewhere, we need to debug. But in the best case, we will get results within some seconds, because yeah, simulation doesn't take long for mathematical functions. So let's see it here. Cool. 2 seconds later, we have our results. How you can access these results now? First of all, if we just take a look, this is just like, yeah, whatever. If you want to see real results, I mean, you saw it here, we put it to F, and like the logic is the same. The class results inherits F. When you come to it, you see here, these are all Pareto optimal solutions. So you don't get all results here, you only get the optimal ones, because 100 times 100, these would be more results than these. So these are only the optimal ones. One individual, next one, and so on. And we can do the same. Let's go down. We can do the same if we want to have the matching inputs. We just look at this. So this first individual has this performance. Yeah. So this was it about coding, but yeah, I love results, so let's jump into results as well. I love to use Plotly for it. I don't know, others prefer matplotlib, but let us just see how the results look like, and then we can compare it to the real results. But the programmers of Pymoo really did well. Like if you compare it to any other package on the internet, it outperforms it. It's much faster, the results are better, and they really have a lot of extra gadgets like constraint handling, parallelization, everything. So if you want to optimize with a package, always use this one. Let me plot it fast, and yeah, afterwards I wish you happy coding. Super interested. Also in the comments, let me know how you feel about the package, if you liked it to implement, or if you found it a bit not scary but complicated. One last thing for plotting, you saw now here the results are in this shape. To plot it, obviously we need to transform them first, so it was the last step that I forgot. So let's call it result data, and yeah, we plot it here first, but results dot first and then we just transform it. Yeah, I mean, it's a numpy error anyway, so it works fine. So you see now it's transformed. We have all the F1 values here and then all the F2 values here, and now we can just pass them. We can just pass them here. Oh gosh, I don't know how to copy paste on this new keyboard. Result data. The first one is F1, as you remember, and the second one is F2. And yeah, I don't put any X's now to save your time. Cool, something. Oh, sorry. Let's put the mode in markers, otherwise we don't see anything. Cool. Sorry. Yeah, always the same. Too much things they include or exclude. So cool Pareto font here. This is F1. So this -10 point which you see here is exactly the point that we have here. And it's cool to see that you then have a big jump, and then you have here all the other Pareto optimal font points. And this shape is kind of cool because it's like the shape of, actually it looks like two different functions here. Really like the test function. And yeah, you can go on Wikipedia, search for the real function and how it looks like. These results are really good. Obviously we had a lot of tries and a lot of generations, but yeah, these results are really cool. I hope you enjoyed the video. If you have ideas about it, let me know in the comments. And yeah, sorry that sometimes my typing was not completely correct. If you need access to the code, everything will be also in the comments. I will publish this on a repository, and you can play around with it, have fun with it. I will also let you share in this repository a list of a YAML file and a requirement.txt that you can just install in a virtual environment and get started as fast as possible. Cool! First optimization we did together. I really enjoyed it, and I hope you could follow and also apply it to your problems. Let me know in the comments the next optimization problem you want to tackle, and until then, keep optimizing.